Good morning, everyone. Welcome to the first breakout session of Hadoop Summit for 2014. My name is John Akrid. I'm the CTO of a company called Silicon Valley Data Science. We are a data science and data engineering consulting company that works with a lot of local and US companies to solve hard problems with data. Today we're going to talk about an application that we built, or are building, I should say, that looks at Caltrain. And so you might wonder why a data science consulting company is building a Caltrain app. Unfortunately, this morning was nice enough to provide a lot of examples of the reasons we're doing that. So I don't know if any of you tried to take the train down here this morning, but apparently there was some fun up the line. A good portion of my team takes the train to where we work every day. That's a few of them standing there waving. I'm rather proud of this photo. That train was moving at about 40 miles an hour when I took that picture, so I got it just right. But since we take the train to work every day, and I am a real slave driver when it comes to getting to work on time, we were very frustrated at the fact that it's difficult to get visibility into how Caltrain is running at any given moment. And so whilst the world is good at complaining or alerting on Twitter, a sort of real-time status of a complex system like a train network, tweets do not make in and of themselves. So on a more serious note, as a consulting company, we do a lot of work for our customers that we can't talk about in public. And also as a company, folks hire for their expertise with emerging technologies. We need a way to experiment with those technologies on our own so that we know how to apply them when somebody wants to hire us to solve a hard data problem. So we have been working with a bunch of data around Caltrain to better understand how it operates and to help ourselves understand when the train's going to be late and what we should do about it, but also figure we'll release this to the public and let everybody else benefit from it. So for those that aren't familiar, Caltrain is the commuter rail system that basically goes from a little bit south of here all the way up to San Francisco. It's got about somewhere on the order of 50,000 riders every day. It's a little old. There's 120 cars, and about 60% of those are 30 years or older. They don't talk about the engines, which is probably a good thing. So it's a fairly well-used system with a lot of trains, a lot of runs, and it goes up and down the peninsula every day. There's really no reliable information about when a train's coming. If you're familiar with subway systems like DC or other places that give you a nice countdown on when the next train's coming, that's very, very helpful, especially if you're trying to tell your boss when you're going to get in the morning. But on Caltrain, we have some version of that on occasion, but it was out between April 5th and June 2nd most recently. So 2-month outages in that capability. So we thought to ourselves, how can we figure out when the train's going to be late or when it's running on time, and can we build a system that takes advantage of the fact that our office is actually overlooks the Caltrain. If you ever find yourself on a conference call with me, you'll regularly be interrupted by train whistles going by and me hitting the mute button to try and obscure the fact that we have a train 10 feet on the other side of a window. So we can hear the train horn, and we can look out our balcony and see the train go by, and that's a way to figure out how the Caltrain is running of sorts. But like I said, there's also a purpose-built system that Caltrain has an API for that we can use to look up status when it's not having a 2-month outage. And as we showed you, when things go bad, the Twitter sphere responds with information about what's going on. And so we set out to build a system that would allow us to try a lot of the emerging technologies that you can do to integrate this kind of information and assemble some notion of the state of a complex system. So what we're going to talk about this morning is the data science and the engineering that we do to put together all of these symbols, use historical information that we're also able to get from Caltrain to understand how it runs in general. and provide a service that gives users valuable information about how Caltrain is running at any given time. One of our important guidelines as we work is to not let the perfect be the enemy of the good. Any one of these signals is lossy or flawed, and so the hope is that by combining visibility across different channels, we can get a more rich view of what's going on. So, you know, a lot of systems start out with sort of what I would describe as a stovepiped data source, right? You build some kind of system in an enterprise, and you designate a data source for it, and you hook it up. And if that data source goes out, has an outage, you're kind of out of luck. If you depend on Caltrain's API, you are out of luck for 2 months. That is a single source of failure. And so we fundamentally believe in building systems that leverage available data across the different kinds of visibility you can have. I like to talk about driving my car and the importance of understanding what speed I'm going. The California State Highway Patrol has a nice habit of letting me know when I go too fast. So if my speedometer goes out, I'm not completely without recourse. I can look at my tachometer, which will tell me how fast the engine's going, and I can look at my gear shifter to understand what gear I'm in, and I can put together some mental idea of how fast I'm probably going. It's not as good as a direct speedometer, but it's better than not knowing at all or finding out when the little red lights show up behind me and I end up paying an expensive ticket and get a letter in the mail telling me I'm one of the worst drivers in the state of California, even though I've never had an accident. So we try to combine data across disparate systems to provide a holistic view into how something's operating that is resilient to the failure of any one of those particular signals. And Caltrain has been kind enough to provide a heck of a use case for us to test out some of these techniques. So we're at a conference focused on Hadoop, so it makes sense to talk a second on why Hadoop is a wise choice in the first place for this. And for the moment, at least, with 50,000 riders, while we get some pretty decent velocity of data coming at us, and when we talk about some of the techniques, you'll understand that we actually do have a bit of volume in terms of audio signals and the like. Really what we're looking at here is variety, is the Hadoop's ability to gracefully handle various forms of data is one of the things that makes it so powerful here. We're working with audio data from a microphone. We're working with image data from a camera we have out on our balcony pointed at the tracks. We're monitoring Twitter feeds so that when people go up in arms about today's delay, we can notice that. And we're also hitting an API, which gives us a good variety of different kinds of data to work with to reason about the status. So I'm going to introduce my colleague, Tatiana Meskalevich, to talk a bit about the techniques we've used here. Tatiana is one of the data scientists on my team who I get to enjoy working with on these systems, and she'll walk us through the techniques we're using here. Tatiana.
Thank you. Thank you, John. John was actually the reason why we started doing that. I guess he got really tired of hearing Caltrain noises and really tired of people complaining. So let's talk a little bit more about each of those signals or each of the sources of data and how we put it all together in our system. So we'll start with the audio. Since John is actually in his past life had an audio recording studio in Chicago, he had this wonderful microphone at home, and we borrowed it in our office, put it outside to listen to the Caltrain. However, microphone was not be able to connect to our network, so we decided, why don't we play around and get a Raspberry Pi in the office? So we set it up together with a Raspberry Pi. And basically, microphone was converting data from analog to digital, and then the Raspberry Pi collected a digital signal through a USB, and we were able to implement or put Flume agent there to collect that data. Which was a really excellent project for us to get a little bit into open source and also this interesting hardware. So then we connected our Raspberry Pi with Amazon Web Services, and so we created a mini data pipeline there. So what do we do with the sound data? We apply some fast Fourier transforms, and for those of you who may be not really familiar with physics, is when you look at the signal, you represent it over time. But if you really want to detect a train whistle, so you want to look at the frequencies. And the fast Fourier transform has a great method of transforming the signal from the time domain into frequency domain. And since we are sampling our sound, it actually behaves very well for the discrete data. So the next source of data was the image. And that's a picture actually of the camera on our balcony pointing at the trucks. And the setup was pretty simple. The camera is connected to a network, and we use a wget to collect images every 2 images about 2 to 3 images about every second. And it goes into our local server in the office, and we then load it into our AWS setup. And initially, we store it just on the file system since we get so many images. So once we get an image, what do we do with that? We actually utilize an OpenCV library from Python to recognize whether the train trucks actually have a train on it or not. And I'll talk about it a little later when we go into data science component of our talk. When it comes to the Twitter data, it's already been discussed over and over again. Twitter API has a great search feature, and we use keyword, just a simple keyword call train. And we have a Flume agent running in our AWS that collects all the tweets. Here's a preview. We use Apache Storm to process the tweets. And we'll talk a little more later about how we calculated the baseline for the tweets so that we were able to detect events when the call train was late, actually. And last but not least is the API data. And this is our sort of a legacy setup before the APIs went off. We wanted to understand the system itself. So we wanted to collect the data available from Caltrain, and it was fairly successful. So we collected the API data from 511.org, which in this case were a pretty standard format. And we also scraped Caltrain website because API data did not contain train numbers, which was very strange. So if you want to really track the train, there's a lot of fuzzy matching given the lateness of the train and the state of the system. So we combined both of the data, and we actually got pretty good results, not even doing any kind of research or reporting, reading of the reports on Caltrain. Our prediction were that Caltrain is actually on time about 93% of the time. So this is just our pure exploratory analysis of the available data. However, since they were not working from June 5th, we decided to put that source sort of on hold and then re-implement it later into our system. So how did we do it all? We basically decided to combine all the signals that we had available in the last 2 months, so audio, image, and a text analysis, and then we basically wanted to understand the state of complex system. And since we are here at the Hadoop Summit, and we know we all like technology and architecture, so here's the preview of the system we have architected. So we have external data sources. In this case, they're the ones we just discussed, the sound, the Twitter API, the web camera, and the Caltrain APIs. At the moment, since we already engineered pieces, we actually reused our infrastructure, and we used the Flume to ingest the data into our Storm topology implementation. So I'm sure most of you are familiar with Storm, but the Storm is the real-time processing system that guarantees signal processing or guarantees the data stream processing. And it's also very well distributed and scalable. If you look at this picture, you can see that there are 2 components of Storm system. There are green components, which call the spouts. Those are how the streams are coming into the system. So they're basically piping the data into the Storm. And then the yellow components, they call the bolts. It's where the actual data streams get processed and the information is retrieved. And then the actions can be whether you send alerts or you do some kind of processing or image recognition, and then at the end you store it, whether it's on your server or in your data platform. So let's walk through an example here. So for example, for Twitter, we actually have a Flume running connected to Twitter API, and it pipes the tweets in JSON format to the Twitter spout. Then we have two processes happening there. First, we parse the tweets to extract the information that we need, and then we store it in HBase using the HBase writer bolt and topology. The reason why we do it, we like to have a little bit more structure extracted from tweets, and then we also have certain APIs written for our own applications that actually collect data from HBase. And the second part of the tweets processing is the Twitter counter. We realized that if you just look at the simple counts of tweets, people actually don't tweet about Caltrain a lot on a regular basis, unless something really goes wrong, right? So our first approach was, let's just look at the counts. And once we look at the counts, if something is happening and if the counts are above some certain baseline, let the event detector deal with that, right? So counts are streaming to event detector, and the event detector says, whoa, Twitter is definitely blowing up on this Caltrain strategy or problem, or trains being broken, police activity, etc. So let's detect that event and transmit it to our application. As far as the data platform, right now we store most of the data either in HDFS or in HBase, and we also run Cloudera Impala for our analytics and exploratory analysis, and as well as our plan, we are examining using Spark once our data volume gets really large. So let's talk about data science now. So what did we do with audio? And I already previewed a little bit of what we've been doing with the signal. So we first transform it using fast Fourier transforms, and then we identify something called fundamental frequencies. And so the way we build the model, we just use simple decision trees for basically identifying two types of the trains. Where we at on Sunnyvale station, there are two types of trains that go past the station. Ones are local trains that are stopping at the station, and the second one is the trains that actually pass by. So those are either bullets or express trains that don't stop, because Sunnyvale station is not a major hub for Caltrain. So we decided to classify those trains into those two categories to understand at which time the train passed by Sunnyvale station. So the way we do it is basically, if you look at the frequency of signal and if you look at the Doppler effect of the signal, if the train is passing by really fast, you have high frequencies, so the minimal and maximum frequency difference is large. And then if the train passes by slow, the difference between minimal fundamental frequency and maximum is not as large. So based on that, you construct a simple decision tree, and we train this model on available signal every day. And so then we just basically extract minimum and maximum frequencies and send it through a processing in the real time. So once the event detector detects that the train is actually running late according to scheduled data, we basically send this to our application, as well as store this in HBase for further processing for our internal analysis. With the image data, we actually use the OpenCV package, and in particular, we use this ORB algorithm, which is called oriented brief. And what it does is it basically takes, it looks at a snapshot of a surface. And then, for example, when there is no train, it identifies so-called the key points on this picture. And then it looks at the snapshot of the same surface a second later. And once it identifies key points on the second snapshot, it basically counts of how many of those points were the same in the space, right? So on the image above, it basically looks at the different snapshots and counts those key points. So the more key points you have that are the same, that means there's nothing changed in your picture. The least key points you have, that means that there's a significant change. And since we are definitely pointing directly at the tracks, as you can see from our picture, it's very unlikely you have some objects that are not trains there, unless you're in the middle of the night when Caltrains are repairing their tracks, which also happens. And therefore, we are collecting the data and storing that data to identify those corner cases as well. So far, the algorithm has been really successful for us. We were able to identify about 95% successfully the trains on the track, and we also didn't have any false positives, which was fairly good. So when it came to text, there have been a lot of research and writing publications about change point detection and event detection and time. So if you think about the tweets are streamed in real time, right? So you can look at their volume coming up at certain points of time, right? So we didn't want to go into any complex system. We just wanted to start it very simple, right? We have data, and we just looked at the counts. And the way we did it, we basically just took simple model, and we'll look at the distribution of tweets for each hour over a period of time. So for example, this graph represents here a frequency of tweets at 5 p.m. Through February through almost end of May. So you can see that there's a certain weekly pattern there. Most of the people tweet about Caltrain Monday through Friday. Nobody wants to tweet about Caltrain on Saturday and Sunday, unless maybe if you're going to a game, right? So there is some variation during the game time. However, you can see just by looking at the picture, the frequency alone will identify the events. And if you think about it, if Caltrain is on time 92% of the time, this is fairly accurate just by looking at the tweets. So for example, right there, I pinpointed the peak, which was on March 12th, and there were really, really big delays at night, also combined with some BART problems. So we definitely went deviating from our baseline. And the way we calculated baseline, we just use RIMA models that are fairly popular in statistical time series analysis. And it gave us a really good baseline calculation. So we did it for every single hour, and we basically recalculated on a daily basis, and so that our event detector can detect those deviations and see what exactly happening compared to the schedule, and took other signals to actually notify our application if there is an event of some kind of catastrophic failure. So we're here now, we did all of this analysis, and what are we going to do with this? From the data science perspective, and we really want to understand how can we catch the direction of a train, and we've been experimenting a little bit, and I think for us, putting several microphones on our balcony would work, do some physical properties of a speed of sound, and a Doppler effect. So that's a work in progress right now. I think Twitter could be utilized more, where we can classify events better, because there's different levels of delays, and as well as different causes of delays. Like for example, today, nobody really knew what was happening, so people were asking, where is my train? But if you crowdsource, you probably can figure out where it is and what's happening to the Caltrain system. What we want to also do is evaluate the different computational frameworks. So for us, we are really curious in how Spark can come and play, because we're collecting a lot of image and sound data. From sound data perspective, we only have one microphone and getting about 7, 8 gigabytes of sound a day. So we really are curious to see whether we can somehow contribute or use the algorithms that are already available in Spark streaming and Spark processing on the machine learning side to help us to solve the problems like calculating Fourier transforms or recognizing images and so forth. And this brings us to the next point. We do want to add more observational posts. We ask everybody every time we meet somebody, do you live by the Caltrain? Can you see the tracks? Can you hear the train? So if you are, for example, work or live near, please come talk to us. We'll put our setup on your balcony and collect more data that way. And last but not least, we want to give it back. So we want to actually create a Caltrain Writer application that has the information that we're all interested in. I just taken the Caltrain. I am absolutely curious to know where my train is when it's not at the station. So I let John talk more about that in detail.
So I take the train about half the time. Katsiana just moved up to the city, so she's now doing it every day. So she's about to become keenly more interested than I am in having this all work. But you know, like I said at the outset, we don't want to let the perfect be the enemy of the good. So there's a link here to svds.com/trains where you can come sign up for the application. A little disclaimer: this is a research project. You know, so we have one observation post, and there's techniques we can use based on the observability we get in Sunnyvale to say that if the train is, if the express that just went was 5 minutes late at Sunnyvale, we have a pretty good notion, absent any other intervening events, how late it's going to be when it gets up further up the line to San Mateo, for instance. So by integrating a bunch of historical data, we hope to make these predictors not just useful to say, hey, we've made a real-time observation, we're going to share that with you and give you some insight, but also to start taking advantage of deep historical context to make that possible. So, you know, you may have noticed on the architecture slide that Tatiana showed that we have a bunch of things that, you know, you don't always see at the same table, so to speak. So if you're using Impala for something, having Shark right next door is perhaps a little strange because those are often alternative solutions to one problem as opposed to two things you might throw together in the same architecture. So like I said, we're a consulting company. We're experimenting with these things. So we do this stuff in addition to helping ourselves understand when the train's going to come. We want to understand what are the relative strengths of a Spark versus a Impala in that role. So on the one hand, we're working with MadLib on top of Impala to do a lot of machine learning to do some of the predictive stuff that I just described. And on the other hand, we're starting to work with Spark to use MLlib to do some of that as well. The point being that in the Hadoop ecosystem, we have a lot of fantastic tools available to us to do a lot of this data science. It allows us to cycle through techniques and try things like different, you know, random forest algorithms or just simple decision trees to do some of the classification tasks that Tatiana was talking about. And at the end of the day, it allows us to hopefully do useful things. So coming to a app store near you at some point, we hope to turn this into an application that allows you to both get better visibility into what's going on right now, better plan your trips, and if you're local and you know what the available Caltrain app universe is like, it's not a very high bar to surpass. But simple things like saying, hey, look, you know, you're at a station, you might not realize that there's an express that's coming 5 minutes after the local that'll actually get you to your destination faster. Actually, we had someone start working with us and had to call in late on his first day because he started in Palo Alto and got on a late express and wound up in San Jose because he couldn't get off in Sunnyvale. So data science is great, but there are also very simple things you can do by providing an integrated view of information in a simple form to help folks plan. So with that, we thank you very much for your attention today and your time. We started a little late, so we're coming up, but I think we have a little built-in time at the end, so we'd be delighted to take any of your questions about the architecture, the technique, or the approach we've used. Yes?
So in the spirit of scaling things up, talk some either methodologically or architecturally about how you apply this with Amtrak network.
How you would apply this with?
With Amtrak network, where you have mixed use of tracks and dead spots effectively.
Sure. So the question was, I'll repeat it. In thinking about things like scaling up, how would you apply this to a much more complex network like Amtrak, which in addition to just being larger and having more going on, has things like mixed use, so freight trains as well as passenger trains going on the same network. So the immense benefit of these technologies that we've chosen is that, of course, you said scale up, and I will say scale out, right? Which is to say that we can add more observations, we can add more audio data, and the cost of doing so remains largely linear. So on the off chance that I've accidentally gotten myself into the commuter train app business, instead of doing a fun R&D project, which wouldn't bum me out, I don't suppose, you know, it's an architecture that we can scale and apply to that, and the cost to analyze that data stays relatively constant as we expand it, right? So the scale-out property is critical, and all of the technologies that we've chosen up there share that property. So Storm, Kafka, things like that, as well as the core Hadoop infrastructure and the things like Spark and the machine learning libraries we run on top of them all have that scale-out characteristic. In terms of distinguishing between freight trains and passenger trains, while we haven't prepped on that question, I would say that the audio stream would be one very, very useful way of doing that. Freight trains tend to move slower, so you'll have less Doppler effect. Now you need to distinguish sort of those fundamental tones. They also tend to be heavier when they're loaded than passenger trains, and finally, they tend to be a lot longer. But any other technical thoughts on how we might distinguish or understand that aspect of the network?
I mean, we're working with a particular use case with the Caltrain, for example, but you know, even use an image, right? When you take an image of freight train versus image of passenger train, there's going to be significant differences, and we are utilizing very simple devices, right? Just a simple microphone and not a simple camera, just a regular webcam you can buy at the store, and I'm pretty sure with the more sophisticated devices where you have a higher frequency resolution as well as the higher image resolution, you'll be able to achieve that kind of recognition. And I mean, we build this architecture in pieces and put it up together in a scalable manner. So if you can just keep adding those sensors everywhere, and you know, Hadoop provides this nice platform where you can put all of this data together to analyze, you can definitely scale out. But if you want to discuss this afterwards in terms of tracks, we've been talking about it when trains switch tracks, and what do you do about that? I'll be gladly available later to discuss that with you.
So and Tatiana just made a great point of why data science is best a team sport. I went straight, I'm an audio engineer, I went straight for convoluted, weird ways of doing that with audio signals, just like I wanted to do direction with distance and speed of sound, right? 2 microphones, you can tell where it's coming from, and then somebody pointed out, wait, we could just look. The camera might be a really good example of that.
Yeah.
So.
All right, next question.
Yes.
Comment just very briefly on the key differences between Spark and Impala for your application.
Very good question. For our particular use case of Impala, we currently use it for mostly exploratory analytics and for the MATLAB libraries that they have available. So we'll look through those models. As far as the Spark concern, we haven't implemented it for our use case because from my own research, their machine learning libraries don't contain the image recognition and like Fourier transforms, and that's why we deployed our Storm topology, because we were able to be language agnostic and utilize the packages that we had available from Python. Since it's an R&D project, so we have to allocate our resources, right? And we want to keep things simple. So when it comes to comparing side by side, we can discuss that later, but I guess those are 2 different purposes that we're going to be using. They are in the same box to say this is for the analytics, so for offline analytics. So for example, we used Impala extensively to understand the state of the system using Caltrain APIs, because we could query a lot of data really fast. Yeah.
Yeah, I mean, so the machine learning, well, the algorithms available to you in something like MLlib or MADlib on the Impala side are somewhat different. So depending on your use case, you'll have one or both may have a good fit in terms of the algorithms that are naturally good to use. One of the reasons we're curious about Spark is that given some of the developments they've done in the architecture and things like that, we're able to potentially use that as the stream processing component as well. So whereas in Impala we're using that in sort of an offline exploratory and model training in batch mode, in a Spark world conceivably we could take what we do there and deploy those models in a sort of micro batch or streaming mode much more efficiently. So that's one of the things we're very excited about with respect to Spark. At the moment, they're both very relatively new platforms that have overlapping characteristics, but both of them are in rapid development. So even if we had strong conclusions from this, I wouldn't expect them to stay relevant for very long, is I guess the best answer I can give to that. Sure. Well, so the other thing our office is near is the airfield over Moffett.
Yeah, Moffett.
So we do occasionally get helicopters flying over and large or fast fighter jets going over and things like that, which can confound the classifiers, maybe even more than a Mockingbird. And occasionally when the Apple bus is in the public bus stop space where the Sunnyvale bus wants to stop, they honk at it, and that's actually the closest thing to a false positive we get, because apparently the Sunnyvale bus drivers don't feel very good about Apple's bus drivers, but that's a different story. So resolving the fundamental frequencies and really being able to isolate the fundamental from the harmonics is a good way to disambiguate sounds that to the human ear sound fairly similar, and that's, we're always looking at the output of that classifier and understanding if we're getting anything. And that's, to your point, all of these give you something of a notion, but it's by combining what we observed with the video stream with the audio stream that really allows us to get more confidence about what we're able to say with both. I think we have 2 minutes, so one last question in the very back corner. The question is, are there commercial use cases that share the characteristics of this use case? And at the high level, any state of a complex system, so smart grid comes to mind, transportation networks on highways are very well sensated and things like that now and the like. So anything where you've got a combination of intentional visibility and latent signals and things like the social media space where you want to gain that visibility is a potential use case of some of these components. But we picked this because of its general applicability to a lot of industrial Internet of Things and that kind of use cases. So with that, I'll thank everybody for taking the time to listen, and we'd be delighted to talk about this more with you if you'd like to after the session. Thanks again.